Okay, so I am the Director of Engineering, and my main role is to assist the technical committees, or my department is out there supposed to help you, the technical committees out there, get your work done, and actually assist TAC in the administration of those technical committees, and then help get that information out to the general public. This particular session we've been doing for a little while, and I've been helping out for a while. I used to be a consulting structural engineer before I came to ACI, so when I got here, I've been here almost 20 years now, I learned everything I did wrong when I was a consultant. So sometimes I'm able to give you a little bit of, this is something that maybe isn't so obvious. Sessions are sponsored by Baker, CTL, JSW Stud Rails, Sika. Great. Thanks very much if you're in the audience or a representative is in the audience. And of course, our learning objectives have already been more or less stated. I'm here to introduce you to materials on the topic, where you can then find those materials later, which is kind of right out of the bat. Address things that and which this presentation is going to be is, I don't know where you're at, maybe I'll ask you a little bit. Have you ever designed an anchor in your life or not? I purposely went through and scrubbed many equations. So you would not look at equations and you would not look at variables as I talk and try to figure out exactly how it fits into the many problems you've had. Really wanted to do is introduce you to and give you visualizations of the modes of failure, the different types of anchors that we have out there, specific things you should know about those anchors, and get a visualization, and then really start to talk about what is anchorage to concrete, and then how can it go into or blur into regular reinforced concrete. And so anchorage to concrete. So we already talked about overall objectives, and I'm going to start right off with what we're going to be covering today is what's in 318.19, particularly Chapter 17. Chapter 17, anchorage to concrete. It is for anchoring anchors into plain concrete. Understand that. Plain concrete. Now we will talk about anchorage reinforcement, anchoring our different concrete breakout pieces and stuff back into, so those are specialties that we can do. But I want it to get into your head that most of what we're talking about is centered around a big piece of plain concrete, and we're pulling the anchor out or shoving it towards an edge. And then we can make life better by using reinforcing steel. But that's the basic premise of Chapter 17. Now, it leans heavily on Chapter 2 for definitions, which we'll talk about. And then, of course, when you get into, for those who are not very familiar with ACI 318, Chapter 26 holds all the stuff that we want to put into a specification. So the specification information that is most important to ACI 318 is all shoved into Chapter 26, and yes, there is a section on anchorage to concrete. So those are the locations in 318.19 that you should go back to as far as following the code for anchorage design. You'll find constantly two other documents, 355.2 and 355.4. Those are not intended for you, okay? Don't go buy them. They are intended for the manufacturers of post-installed anchors, right? These are the rules for them to get their anchors qualified. Now, if you want to become an anchorage expert and understand a deeper dive into what those manufacturers are doing or what they need to test to, the theory or the actual test, this is where you go. I have 19s up here, but they are finishing up at this convention, the latest version, so it's up to date with the next 318 version that will come out in 25. But once again, when you see this is really intended to the manufacturer. But if you need to take a deep dive, you're getting into litigation. Perhaps you want to go to these documents. We do have this thing called the Reinforced Concrete Design Manual. It's a 2-volume set. We have over 20 worked examples of anchorage design, which should take you through all the paces. every time we come up with some other really unique thing, we put it in there, right? So if you're really just looking for worked examples, Volume 2 is the one that has all the worked examples. You could buy it separately. That's where you'll find that kind of gem of information. We have had SPs over the years that are nice. Once again, these are the foundations that we got our requirements from. Once again, how much of a deep dive do you want to take? You don't really need to memorize this. You can go onto our website, and we have a thing called an abstract section. And under abstracts, you can just type in Anchorage or SP, Anchors, SP, and things like that. You can search by SPs, and you can find all this stuff. But if you want to take a picture of that or something, that's fine. So the presentation, a fellow engineer at ACI does a lot of these presentations, and I took a lot of his multiple sets and tried to boil them down into something that you would enjoy. But he does this work with a guy from Stuttgart, and so I thought I'd give a nod to them. You can get these on Amazon, and you can just type in Stuttgart Symposiums on Anchorage, and these things will pop up. I think they're about $100 a piece. Once again, deeper dive on research. And then for myself, and I will bring them up as we go through this presentation, things like side face blowout. If you don't meet the requirement, the code doesn't really tell you what to do next, right? And the answer isn't obvious. You will find some sort of answer in this book, Anchorage in Concrete Construction, which is Aligahausen, Millet, and Silva. This is John Silva, Rolf Aligahausen, and one of his students, I believe. He's now much past that. It's a long time ago. But anyways, those people, this document right here will kind of fill in the rest of the cracks. So I highly recommend that if you get into it that much. But we're not going to do that today, okay? I will talk about definitions, history, behavior, and theory, and then we'll take a little break to talk about things, maybe get a glass of water. So this is kind of just, let's dive in a little bit to see what we're talking about. So as you can see here, anchors have been around for a little while. How we define what the different types of anchors are back in our definitions. And so that's what I was talking about earlier, why definitions are so important. So adhesive anchors, post-installed anchors, expansion anchors, those types of things are all defined up in front in terminology if you're looking for that. And then, of course, all the variables using all the equations are in the notation section. So let's talk about the types of anchors first. So, I mean, if this is too basic, maybe, but on the other hand, I didn't realize there was all these different types of anchors. So cast in place, new construction, we all got that, right? We all understand what a headed anchor is. We put that in. We have different types of mechanical anchors that perform to various degrees. We'll get into that a little bit. Then we have bonded anchors, adhesive and grouted, and screw anchors. Screw anchors just came into the code in 19. Screw anchors is where you drill the size of the hole just to the size of the shaft, and then you carve in, you screw into the concrete, and it screws right into the concrete wall to make so it's a structural. It's not like a Tapcon that you buy at Home Depot. It can be up to 3/4 inches diameter. It's a sizable anchor. And then grouted anchors are not covered, but they can be successfully used, and we'll talk a little bit about that, but it is not covered by the code currently. Cast in place anchors a little bit. One of the key things that we'll talk a little bit later, I don't want to get into variables, but when we do talk about pulling an anchor out of the concrete, one of the key variables that is important that drives a lot of the design is the effective depth of the anchor. And the effective depth is always where that anchor, the bottom of that anchor, is providing a force. So as you're pulling it out, it's that force down at the bottom. It's where it is bearing. So it's always on the top, like the top of the nut, the top of this J, the end of this hook. It's in the base of the hook. And even when you have an embedded plate, It's from the concrete surface down to here. And it's important to understand that. I'm not going to keep doing this with variables, but the effective depth is an important concept that you should understand. When we get into post-installed anchors, it gets a little more complicated, and you're not going to say, well, where's the effective depth? Well, any manufactured anchor is going to have to be tested to 355.2 and 355.4, and what comes out of that document are key variables. One of them is H effective, okay? So if you choose to use a particular anchor, you're going to have to get that cut sheet, and they're going to give you all the variables you need to run the numbers in 318. So this has taken decades to kind of get that symbiotic relationship to occur, that we are getting the values we need to safely design by 318 using a commercial product. And one of those factors you're going to get is H effective, okay? So one thing I want to say here, there's different types. We'll go through a couple different types of post-installed mechanical anchors. These are displacement controlled. So, okay, you put them in, either you pound them in, or you put them in and you screw all the way down and you walk away. You cannot further tighten that post-installed anchor. The bad thing about that, it's a good anchor. All these things are good. I'm just trying to give you the limitations of said anchors. So the thing about this is cracking is something we need to consider and understand. And there's a fundamental shift in how we treat anchorages in concrete, and we'll get into that in the history in a second. But understand, if you're using a displacement type expansion anchor, once you put it in, there's no further adjustment. And so if cracking becomes a big issue on your structure or your application, you're going to lose your strength very, very quick in this type of post-install anchor. Then we have torque controlled, means, okay, we put it in, we can tighten it, but if it cracks, you can actually further tighten it. You have the ability to go back and further tighten your expansion anchor. So if you have the wherewithal or the concern, or there's something happen and you have these type of anchors in the field, you have the ability to bring it back up to a better capacity. And the best mechanical, post-installed mechanical anchor, what these called are undercut anchors. And so that's where you drill a hole, then you have to go in and drill again, so there's an extra step, and you cut a wider, like a bell, like you do, you ever heard of these things called bell caissons or something like that, where you widen out the base at the bottom. That's kind of what you're doing here. You're widening out the hole, and then when you put the anchor in, it goes in, and you're actually kind of getting that headed anchor that you might have cast in. It acts very similar and does extremely well. But it's more expensive to use because both in construction and historically they've been more expensive, although I haven't looked at cost in a while. In bonded anchors, we have two types, adhesive and grouted. So let's talk about grouted first. Usually the hole diameter when you drill it is a little bit greater than 1.5 times the bar diameter, and basically you need some sort of non-shrink grout. It's got a lot of black eyes over the years, largely because two things. One is hole preparation, which is a problem with any post-installed anchor. Hole preparation is everything. It's one of the everythings. And then, of course, the type of grout you use, and if it shrinks away from the sides of the either the screw or the sides of the hole, then, of course, it goes away. However, they have been used very successfully over the years. So it's just something, I guess, we haven't quite been able to pin down as well as the other types of anchors. So when people do use them, they generally use it, in vertical down installations. Usually use a headed rod or headed reinforcing bars. And I think you can get this presentation online afterwards. This is being recorded. You can take a picture of that if you wanted to. But there are guidelines to help you understand how to use these effectively. Once again, if you got on the internet or you go to, here's Structural Journal. If you look up Cook. Robert Cook. That's not Robert Cook. Ron Cook. Look up Ron Cook. You will find some directions out there on how to use a grouted anchor if that is something that you're really interested. Adhesive anchors we do cover, and they have a little bit tighter hole, largely to save a little bit on the epoxy. And the biggest problem we generally have with adhesive anchors is we get a bond failure. And once again, the reason why the biggest problem with why we get bond failures, with the hole. We didn't clean out the hole properly. We didn't do what the manufacturer told us to do. But it has a lot of black eyes, and yes, we will talk about the Boston Tunnel today a little bit, just because we're in Boston, right? And really what accelerated putting mechanicals or post-installed anchors into ACI 318. So anyways, done correctly, wonderful product. Usually we use a threaded anchor, and and we usually use a cementitious kind of filler, or a polymer filler. Once again, you're going to use whatever product that you purchase, right? You're not going to go out and choose your own product. You're going to get the product that this manufacturer tells to use with the anchor that they're going to give you. And other things that have come along in recent, as far as anchors are concerned, we have shear lugs. I'll have that at the very end of the presentation. Just introduce to you what they look like, what they do, how they behave, and concrete screws, which I kind of briefly mentioned, which is how they go in and they literally screw themselves into the walls of the concrete. And things that are not covered, other anchors you might see. So you can start to tell there are many products, many ways to anchor, and it can be quite daunting, and each one has a little bit of a difference from the other one. So as you get into this, right, you'll just have to kind of start with one, use another. Necessity is the motherhood of invention. You're gonna design something, you're gonna cast in place something, and they're going to say, well, that's in the wrong place, and so they're going to cut the top of the anchor off, and they're going to want to put in a post-installed anchor on you, right? So you're going to get right into it. But, like precasters, they love these specialty inserts and coils, but we do not cover that in the code. Through bolts, we don't cover. Now, often I get questions on through bolts. You can use a lot of the principles, and you're going to get the visuals today to help design a through bolt, but the code does not really help you on that, or does not have any code requirements. Sometimes you'll see this in very popular and more industrial jobs. You'll see here at the bottom, you'll have anchors that they set out of the top, and they come down to some sort of plate. In this case, it's a circular plate, and they're using all those anchors touching that plate, and they're wanting that plate to kind of expand the bottom before, for your breakout, to increase the breakout angle. Well, it doesn't change the angle, but instead of the breakout starting at the nut, it'll start all around that perimeter. Now, we don't really have any direction on that. There are lots of papers out there that you can go find, but, we're kind of on your own. Channel anchors, at least, I do believe ICCES, I think at least has some acceptance criteria, and therefore there's some manufacturer products out there that you can at least go down that route to use channel anchors for capacities, powder actuated fasteners, and grouted anchors. So those are anchors we do not cover that are steel based anyways in the code. So a little bit about code history. Prior to 2002, so in 2002, we brought in Anchorage, and it was called Appendix D, okay? And before that point in time, you went to several places to get your information. ACI 349 had some guidance, that's the Nuclear Structures Code. UBC had tables in it, which made their way into the ICC, which we later removed because the factor of safety was anywhere from like less than 1 to 8. It was just general practice, and they put it in a table. And the key thing here is first of all, they used 45-degree concrete breakout cone, and they considered everything to be, they only looked at two failure modes, and that was concrete breakout and the steel failure, and they assumed your concrete was not cracked. So that was the state of the industry coming up to 2002. In the 90s, this thing called the CCD method, and I just blanked on what the CCD means, but it's called the CCD method, and over a lot of observation over time, they noticed that that angle was really 35 degrees, and we're going to see a lot of pictures today that enforce that, or reinforce the fact that it's truly 35 degrees, and like I was saying earlier, that comes off the edge of your, in this case, the headed anchor. And so like I was talking about, if you put like a plate down here and you had multiple anchors, like that circular thing I was showing you, you could see how you can get, a much bigger concrete breakout cone. But once again, that's not really covered. So we've switched now to this 35 degrees, and our values are going to be based on cracked concrete until you feel comfortable that it's uncracked, and then you can get greater capacities. But the default is you are putting your anchors in cracked concrete. So 45 degrees, 35 degrees. The equation difference really wasn't all that much, just pretty much this K factor, which, of course, a lot goes into that thing. And then we went from a square root of 2 to 1.5. So it wasn't like a big difference in equations where you didn't have a big learning curve. But the difference nonetheless. This is a little bit old. We'll see embedments much greater than 11 inches. Well, here we got our number. I guess it's number of 11 here, 9, 6. Up to 48 inches, we have got lots of information up to 48 inches of depth, and we still see the 35 degrees. So that said, we get to 2011, and we had not had anything. We just had mechanical anchors that came into that code. We had not had epoxy anchors, and of course, after 2002, or just around there, is when the big dig thing happened, right? That was an adhesive anchor failure, and the National Transportation Safety Board said, hey, you guys need to solve this problem now. Well, it took us about 10 years because we weren't even working on it, but then it became a top priority, and so anyways, adhesive anchors came into it, and basically it says, and if you're installing an adhesive anchor horizontally inclined or up above, we also require that the certifier be, that the installer be certified. And we actually have requirements for inspectors to be certified. Why? Largely because of the Boston dig, and doubly why? Because when you install an adhesive anchor, there are over 20 different mistakes you can make in the installation of that anchor, which will affect the strength of its installation. 20. I don't know if you can name me one just sitting there. So, I mean, it's a much bigger problem than people think it is. And so anyways, so that's why certification, it was a big deal, because the code had never required certification for anything else in the past. And that was a big change. But they said, we'll not allow this in the code unless people know how to install these things. All right. In 14, there was a big reorg, no major changes. And in 19, we added screw anchors and shear lugs. So that's basically the history of how the CCD method has come into existence. So anchor behavior. We'll talk a little bit about cracking since we actually already brought that up. We're going to go over this. We're going to go over each one of these failures later, so we're going to first introduce this in the overall introduction. But we have these different intention, we have these different types of failure modes. So now we're kind of getting away from, in how 318 works, we're doing the beam, we do this, we do our design, we make sure, that it's safe, it, exceeds the strength, exceeds the loading, and then we put our reinforcement in very particular ways, but we don't really have kind of like a checkbox, kind of like in steel, where I got to address this mode of failure, that mode of failure, that mode of failure. Well, this is much more in that type of design way of thinking. So we'll be checking steel, concrete breakout, pull out, side face blowout, and bond failure. So each one of these things we'll go through. I'll be bringing this up several times. And in shear, it's a steel failure, concrete breakout to the side, and a pry-out failure. So we'll get through all that. I want to talk a little bit about cracking and why it's so important and why we went from why it was from uncracked concrete to cracked concrete, is because when everything's nice, you get a nice pull out here. As soon as you get a crack through it, obviously you can see how the patterns change as far as how that stress comes up, and it creates a reduction in the capacity. And so here we can see just quickly, you have uncracked concrete, and you have cracked concrete for a cast-in-place anchor here. So you can see that there is a reduction. So these are the values that we're shooting for in the code. Unless you think you don't have cracked concrete, they do allow you and give you factors to increase the capacity of that anchorage design. This is that post-installed anchor that you put in. You cannot retighten. You lose like 50%, fully expanded. Let's say you put it in a little bit, like 50%, even the reduction is even much less. So these things are kind of cautionary here, we're trying to tell you. And I'll get into a little bit the value of which we're trying to target when they give you values. Manufacturers give you values. And you can also see here, if I have a epoxy anchor here, if I get a crack and it goes right through the epoxy, basically I can lose up to half of my capacity, right? Depending on how that crack goes in and around that anchor. And so this, sorry, you're going to get this a little bit. I didn't know what kind of size screen I was getting, so I went to a shorter screen and I didn't catch everywhere the movement of my little arrows and things like that. This arrow is actually supposed to go over here to the edge, but in essence, at 0.015 inches, we basically go to 50% of our capacity for, which I already talked about, adhesive anchors. Okay, so concrete does crack, right? So we want to address that. We do require that in 355.2 and 355.4, that we do make them test with a crack, and that crack width is 0.012 inches, basically the thickness of your fingernail. So if you're out there and you're just kind of walking along, you're seeing cracking, and you put your fingernail in there, and it's much larger than your fingernail, you probably aren't meeting the capacity that you designed for. Okay, so, but they are good up to that thickness or with the crack. All right, so there are limitations in the scope, and that's in the beginning of the section. When you look in Chapter 17, we'll just go through a few of them here, and then we'll have a small break. But one thing they don't want you to do is no removal and resetting of post-installed anchors. So they don't put the anchor in and take it out and put it back in again. All right? We have a beautiful picture when we're trying to explain the certified installers of like when you put the epoxy in the hole, and they had this camera on a group of workers, and they were trying to do such a good job. They filled the hole with epoxy, and they put the anchor in, and they took it out to make sure it was all covered, and they shoved it back in again. And meanwhile, all this epoxy is just going everywhere. And it's just like, no. So in general, it's not, you can't install it, uninstall it, and put it back in again. So adhesive anchors, post-installed anchors, they're hard to predict. That's why, from just general knowledge, manufacturers make make new products all the time, especially when it gets into mechanical anchors. We need them to test, to give you all the capacity or get you all the variables we need. There's no way for us to give you a way to predict a mechanical anchor or a post-installed anchor's capacity without them doing testing. The variability is just too high. We don't cover high cycle fatigue or blast. Reinforcement used as part of an embedment shall develop length established. So you can use reinforcement as anchorage. That's okay. Its effective depth, so to speak, or HEF we talked about earlier, is the development length equations that you use in 318. So you need to, if you want to use steel reinforcement, you can use it. Put it into the length of development. But you do need to consider it for breakout failure. And I'll have a beautiful picture later that will kind of really ram it home what I'm talking about here. And now we'll kind of go on and talk about anchorage reinforcement here. Well, I'll do it, I guess, in a second. Other things is the loads used from elastic analysis. Yes, you can do a plastic analysis. There's a lot that goes into that, but you need ductility in your anchor groups. And one thing I'm not going to talk at all about today is critical spacings and edge distances and things like that. Those are basically spacing limitations you have to live with. A lot of mechanical anchors, when you put them in, they put a wedging force on the side, and therefore there's minimum spacing requirements and edge distances. Those are just restrictions that you'll have to get to know over time. Some of them are in ACI 318, and some of them will come from the manufacturer's cut list. And as I said earlier, for adhesive anchors that are installed horizontally, upwardly inclined, or overhead, always have to be qualified by 355.4, and you have to have a certified installer. A lightweight concrete has unique reduction factors for lightweight. Just know that. It's different from the ones that we use throughout the rest of the code. So just whenever you see a lambda A, know that that lambda A is referring to anchorage design. That's all you really need to know there. We do have general limitations for casting anchors. We just don't have test data enough above 10,000 PSI. That does not limit you from using the anchors in concrete greater than 10,000 PSI. But in your equations, you can't use the number greater than 10,000. Post-installed, I don't even know what you have. We did try for a while to give some basic information so you can get a preliminary analysis done using post-installed anchors. That's largely gone away. Really, you just have to use what the manufacturer's testing gives you, and they might have something that goes above 8,000 PSI. As long as they've run the protocols and made the sheet, then you're good to go. So once again, these are the failure modes. I have it kind of throughout the presentation. Where do you find all that stuff, the list of that? There's a table in 318 called 17.5.2. They list them again. They give you directions and where the requirements are in the chapter. And so there's a lot of, all this information is really easy to find in chapter 17. We're well over 20 years of using the CCD method. It was incredibly painful for the first at least 7 years, introducing it to the community. And anyone who had to live through it was very difficult. I think we've largely worked through all the problems with, the original anchors, but now we're trying to slowly introduce all these other different types of anchors, which I said earlier are not included. Now we get to the supplementary reinforcement, anchor reinforcement. So yes, the presence of reinforcement around these anchors will increase the capacity of the anchor design. Of course it does. But how it does it is what's important. And so we have two concepts in the code, one called supplementary reinforcement and one called anchor reinforcement. And so let's just look at this kind of a simple thing here for tension. We got a plate, and we have, let's just say, welded studs here, and you can see where here's the tension concrete breakout, and let's say we throw some, in this case we'll call it anchor reinforcement in there. We have a tension load that's going up, and if I want to have some reinforcement to help me out, I need to have reinforcement going in the opposite direction of the applied load that brings that load back into the structure. If I don't do anything to just but provide just general reinforcement that goes in the general direction that is opposite to this, I can call it supplementary reinforcement. I don't have to design it. I don't have to, there's no size, there's no nothing. And you get about a 10 to 15% boost in your values. Okay? So if you're designing like in the top of a pier, which we'll talk about a little bit later, if I've already got, vertical reinforcement, my longitudinal reinforcement in my column or my pier or whatever, and I can put my anchors in, it's there. I don't have to even use it, but I can call it supplementary reinforcement, and I get a 15% boost in a concrete breakout calculation. If I want to use it, which means basically I'm going to negate concrete breakout, or I'm going to stop the breakout from occurring, then I need to develop that reinforcement. This is where you need to understand what's happening, right? What does the concrete breakout look like so that I can predict the crack, so that I can then put in reinforcement to negate the plain concrete breakout failure. And so this is a case where then you would need to, and like this shown here, and this is in the code, I would need to develop that reinforcing steel. In this case, we've kind of got a hook going here. I can make the case that when I do something like this, it's developed right here. But hey, for the purposes of this conversation, I would have to develop here inside the concrete breakout and then develop it on the other side. And if I do something like that, I no longer have to worry about the concrete breakout. Okay? So that's kind of the whole key to all this stuff is, what am I doing? Am I truly in a situation where I don't have any reinforcing steel around? Do I have some reinforcing steel around that I'll take it if I need it? Or do I need to design some reinforcing to actually just preclude the type of failure?
Matt?
Yeah.
I think you have a question.
Oh, yes. Yes, sir.
I've not asked on the previous slide before, I forgot. Maybe I'll ask. But so here, for example, if as long like if there's reinforcement here, I guess for axle load, and the bars that cross that like Anchorage plane, like is basically into like a beam, for example.
Yes.
That I guess would that qualify, or does it need to be a bar specifically like a square loop basically that passes?
No, you're just trying to anchor that breakout. However you do it, it almost makes a little more sense in shear, which we can kind of go ahead to a little bit. Here, we'll get into all this a little bit more, so don't worry about that. But like here in this case, same thing with shear, although shear is a little different, but I think the point I want to make here is, like in shear, like on the edge of a slab or something, I typically have an edge bar, right? And then I'd probably have some mat steel coming over, and it would be hooking down, right? Well, I'm just going to have that there anyways. I'm putting this thing in here. Everywhere it crosses, use the equations in the code, and each one has some strength. It may not have full strength, right? But it's there for you. You can use it then, and maybe I don't even need a hairpin, right? Because the steel is present, and it's in the opposite. My shear is going this way. My bars are going that way, and I'm holding that sucker in, okay? Now, the great thing about shear reinforcement is if you're casting in place, so it's fresh, it's new construction. If you use a hairpin, we call these things hairpins. For those of you who don't know what a hairpin is, you're looking at it, and we call these things hairpins. We use them to spread out localized stresses in concrete all the time. They're wonderful. Whenever I'm nervous about anything, put it in a hairpin. So, but if you put it right up against the anchor right here, that force is directly transferred to this. Okay, so you don't even have to develop anything here. All you need to do, make sure it's touching. And then you can then take it back wherever you need to, however you need to, and shear. So you don't quite got that opportunity with the tension with anchors coming down, right? There's nothing, you can't grab it, right? Okay. So those are those concepts. There's other limitations. We don't cover anything greater than 4 inches in diameter. So hopefully you're not using anything greater than 4 inches. And we have no limitations on H effective. If you go back in time, we used to, that went up over time, and now there is absolutely no limitation on how far you can go down into the concrete. There are limitations on adhesive anchors only because the manufacturers haven't seemed to get out of this range yet. So until they get data and are able to release this range, they do have a limitation. So anyways, that's just that. And okay, so that's the introduction. You've already digested all that food from your lunch, right? So no more nodding. You guys have any questions at this moment? Yes, more questions.
One of the questions I had was, I guess for steel and like bolts or welding space, from my understanding, a lot of the equations almost always deal with just like the dimensions of the cross section multiplied by the strength of the steel. And I guess wondering for concrete, is it very similar, or especially for the adhesive anchors? I'm wondering, is there anything regarding like aggregate size or concrete factor or anything like that?
No, just concrete strength, right? And the interesting thing is, yes, for like steel, I say, okay, I just multiply times the, number of bolts times area of steel, strength of steel, and I'm good. What I'll try to do here next is you really got to think of the breakout failure, right? And no matter what type of concrete I'm using, we're finding that it's always this 35-degree angle. The question is when you put multiple anchors in, how does that affect the size of that breakout? So I could use 100 anchors, but if I bunch them all really close together, I'm really not going to get any bigger breakout, right? So there's rules in there on limitations on spacings and things. And if you space them too far apart, then they become anchors on their own. As soon as you get within a certain distance, which is 1.5 times HEF, less than 2 times 1.5 HEF, then you start to consider them as a group. How's that? Any other question?
Thanks for presentation. Regarding shear reinforcement, if you have a base plate on here, can you use screws and ties as shear reinforcement? And if we can,
yes.
how many of ties in terms of depth of the pier can be?
Right. You're stealing my thunder. I'm feeding it to you slowly. But so the question was can I use the ties? Like if I got a pier and I've got my base plate on top and I got moments and shears and tension and I got shear, can I use those stirrups at the top to take the shear? Absolutely. And you can do it in a couple of ways. One is just think of it, because first of all, if it's closed tie, right, to me, it's developed as soon as it goes around the bar, right? So you got full development of FY of your tile around. So really it's just how many ties do I have to keep in? So we'll talk about different concrete breakouts and shear. I can tell you what the dimensions of that breakout will be. So then you just have to get enough in there, right, to keep it in. Now that's an easy way of just saying that's how I keep my breakout from going away. The other way, which is actually in the design manuals, we did a little strut and tie, if you want to get into something like that, okay? A little more complicated, but if you want to get that tricky, there is an example out there for you. Yes?
I guess kind of piggybacking on that, if you did use struts also for like Anchorage, I guess, or even just longitudinal bars passing that plane, I'm wondering, is there anything regarding like I guess using reinforcement for, like, do those forces interact at all? Like, are you taking away maybe strength from shear by
interaction? Yeah, so, thank you.
Yeah, put it down.
All right, your coat too. All right. Yeah, so the question is how does the interaction occur? And what we're going to get into is you got for the same anchor group, you do have tension, you do have shear. We have an interaction equation that you use to then, it'll tell you, you take the value that you calculated for tension and the one for shear, you combine them by a certain equation, and that tells you the capacity of the breakout. For the steel part, they should be, when you use anchorage reinforcement, they should be in the direction of the applied load. So if one's in tension, one's in shear, you're really not going to be doubling up on the use of your reinforcement in that case, unless you put something at an angle. And if you want to get, then the calculations, if you need it for both, will get a little more complicated. But that's how that would work.
Hey, Matt?
Yeah.
Right there in the back.
Yes.
Is there a plan to add provisions for being able to reapply anchors? Because I know there are products out there where they design the epoxy to be able to unscrew the anchors and put in one time. Like I know Wilting specifically has a product like that where they allow you to unscrew the anchors and put it back in one time.
So the question is the committee going to look at a time when I can reuse the anchor, or at least be able to take it out and put it back in? I know it's discussed. I know that there are success stories. 318, I don't think, they're certainly not up to that not at this cycle. I don't know, before we had Appendix D, back when I used to practice, I just called Hilti, and we talked and talked until we figured out that I feel comfortable to use this product. So, that is where you're at that point, right? At this point in the game. Yes?
So some of the material I read about the different kind of question.
Yeah.
Said that the program managers and the construction managers were pushing for adhesive anchors, and the design engineers were pushing for the original design of expansion anchors. It seems to me that adhesive anchors require a little more inspection, has to be designing a fewer, you're slower. So that seems backwards to me. Do you know anything about that?
Well, the big dig, and we're all moving ahead here, but that's all right. So the question was it, it seems like, and I've heard it go both ways, it takes more time and effort to use one particular mechanical anchor, or it takes more time and effort to use an epoxy anchor. I think contractors prefer epoxy anchors for the most part, but now with the requirement of being certified and stuff like that, that's kind of taken some of the fun out of it. The mechanical anchors are real quick to use, but like you said, some of the less expensive anchors out there, they might not be good, all that great in cracks. When you had the undercut anchors, which is for many structural engineers is their go-to, well, that takes a whole extra step. And that's one that really kills it for the contractor. In fact, I have to drill and then drill again and then install. That's what happened in the big dig. Like I said, we got ahead of things. So okay, one more question and then, it's all right. No, absolutely.
It's only because you brought up the creating, cycle loop for this committee, and then also since talking about anchorage. Do you have any idea what the grade board are meeting and the creating subcommittee regarding anchorage and topic that I'm wondering is
What they're dealing with right now? Okay, so the big thing that is coming in for Anchorage next is deep holes, taking reinforcing steel, epoxying reinforcing steel into concrete, but for a little bit, which we don't really have rules for right now, but even quite deep. And so that is the next big thing coming along, epoxying reinforcing steel into concrete. So that's, to develop it for, basically transfer stresses for, whether it just be shear transfer or whether it be, the continuation. My longitudinal steel busted, and so I'm really going to count on this thing now as my longitudinal steel, or something like that, right? So it's a little bit more. You could probably expand on what we already know to use that product, but it was not official and there were caveats, but now that will be in the code. The rest of the things that are changing are things that will not affect you, just testing protocols that they're tweaking and things, so on and so forth. So, let's just go right ahead. So I'll get right into tensile loading. Once again, we saw these before. We have steel strength, concrete breakout, pull out, concrete side face blowout, and for adhesive anchors, bond. I'm going backwards. Okay, let's just go. So there's a lot of factors that affect tension. We've already talked about a lot of these things. We already said this thing where, when we have post-installed anchors, you got to use the numbers that come from testing, which is done by 3.5.2 and 3.5.4. When we have adhesive anchors, the additional thing we need to think about, there's less things we have to think about because they're not applying a force to the side, and they're not, all the load isn't from the bottom of the anchor, but we still have to do concrete breakout, which is how we calculate regular concrete breakout. It's really these things as bond failures. We have a number of different bond failures, but there's just one equation that you have to use. And as you can see here, and this is what I want to start showing you, is a lot of pictures. If it's done correctly, you get your standard looking concrete breakout failure. This is a case where we had a semi where we lost our bond in the lower half, and then it bonded in the upper half, and so we didn't quite get everything we had. Then we have here kind of a threaded, is a pull-out situation where it didn't really adhere to the anchor itself. Here's another mixed one, and then of course here's just an anchor steel failure. So these are the things that we're kind of looking at here when we talk about adhesive failure. So as we talk about a failure in tension, it is what it is. The concrete was great, it was much stronger than steel. Therefore, we need to make this check. Tons of tables exist out there that you can just do table lookups. Once again, the design manual has these things, and you can just kind of look them up. It's real simple calc over time. When you do this a lot, concrete breakout, you can see that you got your 35-degree angle with a horizontal plane here, so you're starting to see that. You can kind of see it's more of a circular breakout on top. Here's a case of a post-installed anchor. Once again, you're getting that nice 35-degree cone. But when we go to design, once again, my slides got a little messy here. I do apologize about that. But even though it's a round failure, in our calculations, it's much easier to use a square. And so, the difference in this assumption is minimal, but understand, just for your own knowledge, it is actually a circular failure on top, not a square failure. But we are going to use this in our calculations because it's much easier to use. And here's a case where I was saying, you can use reinforcing steel welded to the bottom of a plate if you want to, right? You don't have to use all these other anchors, but when you do, here's a case of a radio tower. We have big guy wires that came down and they were anchored into just big hunks of concrete. And so you can see it's a fairly substantial, this is a big hunk. So here we're talking a couple feet deep and what they did was they didn't put any reinforcing steel for all intents and purposes. That'll maybe we can talk about something else here. But they just basically poured a lot of concrete. They put a little, nice, top bars and bottom bars in it, and this big old eyelet to take the stay wire, and said, okay, it's good. But no, they had these reinforcing steels. They were developed. They went down, and the force got large enough that it actually pulled out of the concrete, and it did so at a 35-degree angle. Isn't that amazing? So this is what happens. Okay? Doesn't matter how big, how small, that is the failure you're getting in tension. And here you can see the reinforcing steel kind of sticking out and how many that they had in there. And one other thing I want to point out here is, okay, so this is a tension failure. I'm sure the load was probably more like this. But notice they did have a mat of steel in the top of their concrete. It is going in the other direction. It did absolutely nothing. So you think your tops, if you're worried about tension and you're putting steel perpendicular, you're getting nothing. And what I want to drive home on that is think of that you're in the top of a wall. Okay, so we got a typical wall, outside wall or something. You know, you put a couple 2 number 4s in the top for nosing, and you put an anchor up there, and they go, well, that should be doing something for me. It does nothing for you in tension. Absolutely nothing. Okay, so this kind of drives home the point that if you're going to provide anchorage or supplementary reinforcement, it has to be opposite the direction of the load here to be of any effect, to help transfer that load into a bigger hunk of concrete. All right, so let's just move ahead here. Then that's out for, you know, where we got, you know, concrete and tension's out in the middle as we get close to an edge. You can kind of see as well, boy, you know, this 35 degrees just keeps popping up. And of course, we have equations that it will adjust for the concrete breakout, and you would have to know, you know, how close you are to the edge and all that kind of stuff, and the code tells you how to do all that. We're not going to get into that. Here's the basic equation and all the things you need to look at. We will not be talking about all of that. But like I said, you know, by what you're predicting and how close it goes to the edge, you can make the calculation. Let's just keep it at that. But one thing, once again, we get back to H effective, and this is something that we'll kind of show again a little bit later. But when you start to get, like, say we're at the top of a pier, or in this case a slab, or the top of a corner of a wall here, okay, and we're pulling straight up, and say we're going down, you know, 10, 12 inches or something like that. In this case, and this is in the code, it's actually 5.5 inches in, and so they're like, okay, yeah, you know, we're going to do good here, we're going to get all of this, and but really when you start to run all your calcs, and the way, this is fairly simple, but it illustrates the point, you actually have to adjust your H effective prime to an assumed failure mode, meaning you're not really down here, you're really up here for all your calculations. And so the code tells you how to do it. It talks about, there's a couple little calcs you have to make here. You got your greater edge distance, you have your spacing, and you come in here and you make a calculation, and you'll find out that the H that you're going to use, H effective prime that you're going to use, is 4 inches. And so what you're doing is you're basically saying, even though I've embedded myself really deep, I have to act as though I'm up closer to the surface, and that's what the code gives you in here. And so it changes all your numbers by quite a bit. All right? So just know when you get close to an edge or more than one edge, you need to adjust your H effective. And we'll see why that's important in just a little bit. So once again, just because you've got a deep embedment doesn't mean that's how you're going to run your calculations. We have pull-out strength, so this is another mode of failure you need to look at. This is fairly easily taken care of, but in essence what we're talking about is that anchor that's down in there, here, it crushed the concrete right above. There was not enough space, in this case, for the load that was applied, for the load to begin to span out. So it crushed it and just pulls it right out. And in the case of like a J-bolt or L-bolt, it just straightened it. So that's actually really easy to fix if you do this for any length of time. Usually a heavy hex head for most steel strings will take care of this. Once you use to the numbers, that's really not a hard thing to preclude. Pull-out resistance for post-installed anchors, once again, are given by the manufacturer, and they change due to diameter and depth. So then we have this phenomenon called side face blowout. So when you have an anchor, a headed anchor that's embedded and it's close to an open edge, there's a lot of force, right? You've got the concrete breakout that's going to occur. And I kind of disagree with some of what some people say, but this is one of those cases where you don't have any guidance when you don't meet the code. I think you're creating a lot of tension in the concrete right underneath here as you put a lot of compression here due to the tension force going up here. And those stresses, tension stresses, have got to dissipate. And if they get really close to here, I think what happens is you get this blowout. Okay? And so that's kind of what's happening here. And really the code just says you need to kind of keep a little distance away from the edge. And it's really not that far away. And you can preclude side face blowout. But the code doesn't really give you much direction on how to design your way out of that one. This slide, which if I didn't torture it in my changing of format, gave you a little way to predict the force. But there are things like in that book I told you from Eligahausen, they have ways to mitigate this if you can't get away from it. And then, of course, adhesive anchors, we already kind of got into that a little bit. You know, a bond failure is by far the, if these things fail, they're going to fail in bond. And so, once again, per 355.4, the manufacturer, they're giving rules that they have to, information that they have to give you. One thing is sustained stresses or sustained loads. Because we are using epoxy. Epoxy is what is keeping it in the concrete. And so they'll have information in there according to temperature and design life. And you know, when you get the cut sheet, it'll tell you about that. And you'll have to, if you have a sustained load issue, there is a sustained load calc you'll have to make. Okay, so if you're under direct tension, that is, and you're using epoxy anchors, that information is available, and the manufacturer has to give you that information. So basically, the default is 50 years with up to 10 years at an elevated temperature. So that's typical for wheelhouse we're going for most buildings or structures out there. Okay. So if you're getting far outside of that, then you really want to start talking to the manufacturer about what temperatures you do have, you know, how often they cycle through, and what the load we're talking about, and they will help you. Okay, so which kind of gets us to the big dig a little bit, and I think I'll just kind of read this because it's more information than I can remember. So I'll just read, okay? And so big dig, here we are in Boston. The tunnel has a ceiling that has air exchange, that is the air exchange plenum. Concrete panels weighing approximately 2,500 pounds are suspended by a system of steel rods and affixed to the tunnel ceiling by stainless steel threaded rods anchored with an epoxy adhesive. The panels were normally 4 inches thick, spanning 12 feet and about 4 feet wide. There were about 20,000 panels in the tunnels. Not all the Boston tunnels used the adhesive anchors. Many used channel anchors. In the D Street portal, D Street, the ceiling was installed in 1999-2000, well after the cut and cover tunnel was constructed. Ceiling panels had to be designed to accommodate suction load of about 45 psf. The anchor service load was on the order of 2,600 pounds. These are the general conditions, sketches of what was installed to support the ceiling of the plenum. As you can see, that was the typical detail. The choice was to go with threaded rod and epoxy. This was what was specified, the undercut anchor. And they said it just cost too much. And what they found over time was a lot of these anchors had pulled away because it was under a sustained load and creaked out of the ceiling. And so this is the scene after the collapse. Looked like this for a lot of the panels. The air intake is above the pedestrian walkway. The anchors supporting the end board and end of the exterior panel are the ones that failed. That is the anchors along line M. So for those of you around here know what that is, it was line M. Further investigation of the hanger support system found conditions like these shown here. The collapse occurred in the eastbound lanes. These photos is of the westbound tunnel in the D Street portal. Conditions like this reportedly existed shortly after ceiling panel installation. Obviously something is wrong with the anchoring system. Ironically, This condition was observed prior to the collapse and no action was taken to investigate. Shown here are 2 anchors from the collapse area. In total, 20 anchors failed along the M1 line. The top anchor has the rod threads with a whitish material that failed when the anchor pulled out of the ceiling. The bottom anchor also failed, but the amount of adhesive that is bonded to the concrete is quite small. The bottom anchor has adhesive in the threads, but not much bond to the concrete. The top photograph of the anchor rod could be classified as a failure of the adhesive at the anchor threads. So that's all I'm going to really talk about that. There's really, the bottom line is they didn't really have any guidance. There's a lot of things that happen in the Big Dig, and we're not going to get into all that, but there was nothing for people to lean on, right? They didn't have a code to go to. They didn't have qualifications like we have now for epoxy anchors, and so that was why we have what we have today, right? Was because of that incident. So hopefully we won't have that problem anymore. But as with any post-installed anchor, we specify it, they buy it, and then someone says, hey Matt, why don't you go through and put 20 anchors in over on line L, right? And I run off and I put in 20 anchors, and then someone says, hey, are you qualified to do that? And I followed the directions. It's the next thing you know, everyone's nervous about the anchors. And so you hear about proof loading a lot. So I kind of threw this in there a little bit. And so proof loading, so well, what do I do if I want to proof load? And so what is proof loading is we just want to make sure the anchors were installed well. We're not trying to establish that these things can handle the maximum load. Okay, so that's not the objective of proof loading. So for adhesive anchors, apply a tension load. Here we go. I'm just trying to go quicker here. When you're inspecting, you want to put in a proof load that's not too high. You want to observe whether there's any yielding or any permanent slip. And if you see any of that, then you might need to do something else. But when it comes down to the actual proof loading, typically it's 2 times the allowable service load or 80% of the rod steel yield strength, whichever is smaller. And the amount of time you apply is kind of up to you. There is some direction here. Silva and Mattis, the Special Inspection Guidelines for Post-Installed Anchors from CAMA. So CAMA is the trade association for basically concrete anchor manufacturers. And so they have some guidelines on how to do proof loading. So if you're looking for that information, I've run into it and I'm like, I have no idea what to specify. So there is some stuff out there, but this is basically what you're looking for. And so if you had to specify something, you would write something like this, which is you're going to test 10 or 25%, depending on what you feel the problem is. And if something fails, if any or more than 10% fail, what are you going to do continuous testing? If you have a displacement requirement. So these are the types of things you're looking for when you want to specify a load testing protocol. Okay, just wanted to kind of expose you to that because it's going to come across on you at some point. So, like I said, remember CAMA has some directions for you. So, anyways. So, into the second module. Yes, sir.
So on your displacement, proof loading, those typically want to include for those that have sustained loads, a criteria for hold time for the load applied.
Well, that's a tough one because that's over time, right?
But that identifies creep.
Creep is dependent on time, okay, and this could be time as years. So really, if you need to make sure that the epoxy you got is what was delivered. If not, if there's any question of that, I don't know if I would even accept proof loading under that condition.
I've done loading and maintaining that load for a duration to determine displacement.
Well, if there's guidelines for that, that's great. I've not heard of them.
I'm saying it was in the specs.
So the thing that makes me a little dubious about that is if I have good epoxy that was meant to not creep over a very long period of time, I could put it out there for months and not see a damn thing happen. So, but there's so many grades of epoxy. How does one actually come up with that criteria? And so I'm a little dubious of that.
My next one would be, you mentioned 50 years and 10 years of elevated temperature. But if you're in a scenario where it's maybe it's a little more rigorous, does 349 point you to something more substantive?
So the question is, if you have a worse requirement, does at least 349 give you better guidance on anchors? No, they don't. Okay. I really think, you have to kind of go to the manufacturer at that point and really start getting deeper into the curves. They're really not out there to get you. They want their systems to work. I mean, they've had some black eyes, but it wasn't always their fault. You know what I mean? So I'm sympathetic to their cause. I do trust them. I do believe it's really not that hard to back up what they're saying, because there's only so many types of polymers that are used, right? I mean, that are used in this application, and so it's not hard to see whether or not you're outside the pale or not. But I don't know of any place where I can get that kind of information other than dealing directly with the manufacturer. Any other questions?
I have a combination question, comment. Will the road test anchors, and I won't get into this sustainability, blackout, but we typically have our reaction flame is twice the embeddment depth, and we do that because it's only 45 degrees failure.
Yeah.
If we got a 35 degree failure,
Right.
it seems to maybe have been proven, or is he restricting that concrete breakout like that?
Yes. So the question was, you're going 2 times in one direction, or two times?
2 times the embeddment depth from the reaction base.
Okay.
One frame is
So it's 1.5. The embedment depth is the distance over. So the breakout cone from the anchor, the cone would go over 1.5. So you're going 2
Now, you go 2 from reaction
to reaction.
right?
So then, yes, you're putting a compression force then on a portion of your breakout. You should be a little over 3 plus. If you truly wanted to get away from keeping a compression field away from the breakout field. Just
The ASTM is twice the embeddment.
honestly, I'm just saying that is fairly well, that's a case where I would like you to go talk to like the 355 folks. And I bet you in 355, I would read in that document, they have some information in there on this. I would look at what it says. And if they feel as though 2 is enough, that they do not, that although it may affect the compression field, or the compression field may affect the breakout, maybe it's insignificant at that point. But I'm just telling you, for me standing here, never having done a proof load test, I would think I would want to be outside it. All right. But we often do things that are practical, and that very well could be the answer, that it's insignificant. But I don't know. Usually I've seen, the 3-point thing. Okay. Any other questions? How am I doing on time?
You got about 40 minutes.
Oh my God. Okay. So
You can end early.
yes. Are you guys getting tired? Do you want to give them the last set of codes so I don't? Yeah. So if you guys want to start leaving on me, you can. Well, all right. So I'll go faster. Shear, not as much. Once again, we only have 3 things we're looking at: steel, the breakout and pry-out strengths. Very similar things that we're looking for in all the factors that we have that are in the equation. Steel failures, it's the shear force. And here they're showing a little bit of crushing in front of, like, say, an epoxy, or in this case it's an epoxy anchor, but this is still considered a shear failure. But the equation you have to do is just the one for steel. I'm just showing you different types of steel failures that you could see in the field. This is considered a failure, so if you're inspecting and you're looking and it didn't shear on you, but that anchor is deforming to this degree, it is considered a failure. We get right into breakout. This is, once again, it's a 35 degrees, but it's going down. Right here we got the anchor. The 35 degrees is coming off in this direction. This force is going this way. You can imagine another concrete breakout going 35 degrees this way, right? So here's a case of, you saw one anchor, you got two anchors. When you have a group but welded to a single plate, you can apply that force to the back, because this is what's all that it's going to grab. It's going to make a breakout from the back set of anchors when you weld your anchors to the base plate, if that's the condition you have. Here's another case of, you can see breakout. You're seeing that magical 35 degrees going out this way, and then we saw it underneath in the other photos. And so this is a pretty straightforward calculation, as we did with tension. There's no magic to it. We're always using this 35 degrees. And we get groups. So let's say if we have groups side by side, if the anchors are close enough together, we have the 1.5, right, towards it's the edge distance here. So now instead of H effective, this distance to the edge is our most important factor that we're looking at, where H effective seemed to be kind of the driving force of our equations in tension. The distance to the edge is what's driving the equations largely in shear. But when they get close together, our path is here, here. It's not here and here. We go straight across and down. And that's how we calculate the breakout plane. And we have three different modes here, so you have to kind of look at how your base plate or your anchor system is in the on top of that whatever element that you have. A lot of times when you have a base plate with oversized holes, if the oversized holes are just minimal, and there'll be minor deformations, you can assume that half of that load will go into the front anchor, the anchors closest to the edge, and the other half will go in the back. Usually you just have to check this, and if this doesn't work, well then either you got to weld the anchors or something, or weld the anchors to the plate or something like that. But this is the most common check if you just have slightly oversized holes. If you weld your anchors to the base plate, you can assume all the load is applied to the back anchor or set of anchors, which gives you a little bit bigger breakout towards the edge. And then, of course, you'll have some situations in which you have to put all the force on the front anchor, and the code in the commentary does a fairly good job of explaining when you might be in which situation. It should be fairly obvious also just from your design. But when in doubt, this is obviously the worst case. Just like H effective, and when we were like in the top of that pier, and even though your H effective might have been, say, 20 inches, but due to the confines of the top of that pier, it might actually only be 4 inches for your calculations. Same thing happens in shear, meaning even though you might be, so if you're in a thin slab and it's not very wide and you're putting some anchor, so let's not think of a thin slab, let's think of a precast panel. Just because I move it back further doesn't mean I'm getting any more actual capacity. I actually have kind of fictitious or a reality distance to the edge that I would run my numbers. And the code's pretty clear on how to run that too. You look at you take the greatest of 3 different things that you're looking at, and once again, my things kind of moved around on me, but instead of being 12 inches to use for my calculations, I would have to use 5.33 inches due to the spacings, the thickness of the panel in this case, and edge distances. So that's all well explained in the code, but it is a key concept because once again, if you're looking at this and say, well, I'm just going to move it back further, you're really not going to get any more. You might have to start thinking about putting some hairpins in, and so I used to do tilt wall design as well. Oh, I use hairpins all the time to start dragging my load away from edges all the time. Just common sense. So concrete, this is shear parallel to an edge. So it's great when shear is going towards the edge, and we do all these calculations, but sometimes we have an anchor that's just sitting right along the edge, and we're pushing along with the side of the element. In that case, we compute the capacity as if it was going towards the edge, take that same load, put it towards the edge, calculate the capacity, and then double it, and then that is the value we get, the capacity against that breakout failure for shear parallel to an edge. So it's a great simplification, an easy check when you get into that kind of a case. Concrete pry out is just when you have too short of an anchor and it's really stiff. It's just not far enough down for it to act, so it doesn't kick out the concrete behind it. I read an old paper that basically if you were more than 4.5 times the diameter of that embedment, you basically preclude pry out. Okay, so just a rule of 5. You just said 5. You should never have that issue. But here's kind of what it looks like when it does happen. It just didn't go deep enough. So it is a check, but once it's a check that you can get taken care of on a regular basis once you get used to the numbers. So there's that, and this last part will go even faster. Any questions at this point? Yes, sir.
Just wondering about the pryouts. You just mentioned about having them on the embedment line. Is that not addressed in 318?
I know it's kind of a nice little piece of information, isn't it? But it's addressed on how far down. I mean, you can calculate the capacity for pry out, or what you get to. It's a mode you check, and it'll give you a number which it will pry out, right? So for the depth, so it'll just be one of the limitations of your design. I'm just saying that once you get above 4.5 D, that number will be so great that it'll never be an issue. Your capacity will be so high, it'll be well above any other of your design issues. Did I say that right?
Is there a way to anchor against that failure? It's supported? Anchor reinforcement?
Well, anchor reinforcement to preclude that? No. That is, so ask her, is there any way to put anchor reinforcement to stop anchor pry out? No. That is simply, you just didn't have your anchors in there far enough. Yeah. So, yes.
You mentioned several times that both the different modes of failure can essentially break out how you're managing the contention planar and essentially going through it needs to like that's the anchor.
Mm-hmm.
I guess I was wondering, I was imagining one situation where maybe you have a wall or even a beam that might have anchors on both sides of the beam. I was wondering
Yes.
if the anchors in any way can interact with each other, like passing each other necessarily.
Yeah, so imagine you had a thin slab and you had both shears going towards the edge, and a plate on the bottom and a plate on the top. Well, yes, they would interact. The code doesn't cover that, but I think what I would do is I'd start drawing my failure planes and start to, maybe use a little common sense. Sometimes what I do is I just throw the code away and I just say, well, what's the capacity of the section? And if I'm just trying to do something silly, I got to stop it. So that's how I would look at something like that. All right, let's keep going. Interaction. So you calculate your tension and your shear for the concrete, the values that we've been talking about. You find the controlling mode, and then you would plug it into here. And as long as it's less than 1.2, you have two approaches that the code allows you. One gives you a little bit more capacity, and you check it, and if you're below 1.2, most people use the trilinear approach here. Equation a little easier to use, and it's less than 1.2, you're done, and away you go. So what happens if anchor reinforce is used? One thing, let me go back just really quick per this graph here, but if the load applied is so low for the capacity that's provided, less than 0.2, then you don't have to do the interaction either. If one side, the shear is just super low or the tension is super low, you don't have to even use the shear interaction diagram. We just say, once you're, below 20% for either one of those capacity, don't even worry about it. But what happens if you use anchor reinforcement? What is implied in the code, which isn't stated outright, is basically if I take away a mode of failure, so if concrete breakout and tension was it, and I get rid of it using anchor reinforcement, well, I don't have to use the interaction diagram, right? I've eliminated that mode of failure, so don't use the interaction diagram when you've already eliminated that other mode. So here's another, just example of where someone didn't really think through all the modes of failure. Right, so this is one of those tramways where the wheels run along on an elevated skyway kind of thing, and so the wheels are going along the plinth, and then they had an expansion joint, and in this case, they have a plate at an angle, and they put headed steel anchors back in here and down here, and they just didn't go through checking all their different modes of failure that could occur. And so what happened after less than 20 uses, 20 runs of a tram, it popped off, right? One of the expansion plates that were embedded popped off here. So they're like, okay, what happened here? Massive. And then I think within, so like I said, just a couple of uses, one went, and then within 5 days, 20 more went. And so it was just, it was just a grossly under-designed situation. What they find out is they didn't design for shear at all. So imagine, yes, if it's just running along and it's providing a downward force, yes, there's just a moment, perhaps, and maybe you got compression on one and tension coming up, but as soon as you try to stop or something like that, where you're producing a shear force, well, shear wasn't checked at all, and so it was, we call these design capacity ratios when we go back and take a look at it. Anything above 1.5 is considered dangerously unsafe. These at 2.0 for shear, for combined shear and tension, it was a 2.2. They go in and figured out that they said that this is reduced, the overturning moment was resisted by, all they did was design the headed steel anchors in tension. They didn't do any other modes of check. They didn't check for concrete failure as a mode, tension to be pulled out, so they didn't look for the concrete breakout even for tension. They didn't check shear at all, nor did they check the interaction. And had they just gone through what the code is telling to you, you look at each mode of failure and is there interaction at the end. And as long as you do that, you will be well. Of course, experience over time will help you eliminate those modes of failure as you do your design. As you started to say things in the very beginning, what happens when you're in the top here, this is a good example of, we got a plate on top of a pier here, and I could say, okay, I'm going to jump right in and start checking for all my modes of failure. And I mean, right away I look at it, well, I already have some steel here, some longitudinal steel. I know I have supplementary reinforcement. I know that I have these things deep in the ground for whatever reason. I mean, if this is what if you have a basic design pattern in your firm or whatever, remember H effective is going to have to go way up here. Do I even bother making the calc? You know, I mean, I know if I'm this far deep and I know I have to go this far deep, or if I'm maybe further up here and I would just go a little further down, why don't I just use this as anchorage reinforcement? It's just sitting there waiting. Why even do the check, right? But you can do the check, but remember your H effective is going to climb way up here. And so all your calcs are going to be off as if that headed anchor was here. And then for shear, question was already asked, well, can I use my ties? Absolutely. You know, depending on how these plates or if this bolt is welded, or, you know, you put washers on top and welded washers, whatever, you know, you could say that your load is from back here or it's from here, and I could just put, you know, three ties at top or 2 ties at top, right? 3 inches on center or whatever. It's probably enough to get you out of the problem, unless it's just a crazy load. In which case, I didn't have to do any of Chapter 17. I got out of it right there. Now, I might still have a side face blowout here. Once again, from just observation, of course, I'm experienced at this. I'll tell you that's not going to be an issue. I mean, you start to get 2.5, 3 inches away from the side, you might have to have pretty big loads to get side face blowout. Okay, but that's just a feel thing you get over time. So I just had this as an example. Of course, this example, I just pulled out a few things, just saying, you know, this in the example, check all your different pieces. This was round. It is okay to consider an equivalent square. Make your equations easier. This is okay. You can do this. Okay, and in this case, you know, just as we talked about, they went ahead and made the concrete check and they brought it way up. Although they did use the supplementary steel because it existed, it doesn't matter that I have to run my equations for H effective prime up here. I still get to use my supplementary reinforcement for my calculations. They went ahead and checked anchor pullout, you know, so they had to get the size of the nut and do all that kind of face. They checked side face blowout. In this case, there are things that, you know, if you meet certain parameters, you don't even have to check it. And then a lot of people start to make these little charts. I've gone through and I checked all the boxes and I said, what is my controlling mode of failure? It was breakout with supplementary reinforcement. Same thing with shear. You're going to check that. They didn't weld the bolts to the plate, and so they're putting half of the force on the front bolts. Once again, you can use square as an equivalent. That is okay. The difference is minimal in your calculations. And you go through, you do your calculations, you make another table, and then you have to check whether or not the interaction, in this case, you know, the forces for the shear were so low that you didn't have to check interaction. But those are the basic steps you would go through any design. I'm saying for this example, you never would have had to do anything. I just kept putting slides in.
You got 23 minutes.
Okay, I'll do this real quick too. And then just so you can see it. So shear lugs, right? We put these big plates, or even better, we could put these humongous H sections down there, and we can transfer a ton of shear at the bottom of a base plate. If you do it, you need a minimum of 4 anchors, and there is, depending on the spacings that you have in there and the depth of your anchor, you have minimum distances. You got to keep those anchors far enough apart so you don't get too much interaction with the shear being transferred out of this lug. So they have some real easy spacing requirements as far as a minimum depth of the anchors you have and how far apart they have to be spaced so that this can be fully effective. You have to have observation holes. You know, you're putting this thing in, and you're filling it full of concrete, and it's going to have to come in and around, and they want to make sure that you can make sure that as you're casting this, you can see that that concrete really is getting up underneath that plate. So they require to have some vent holes or portal holes to look at it. When you use a shear lug, you are going to have overturns. So you're going to have a little bit more tension on your anchors. So know that you'll have an extra step. You'll have an additional tension on your anchors. The failure modes is one is in bearing, and that's a crushing. So on that shear lug that you have basically a crushing of the concrete, and the failure mode goes up. So you need to get enough bearing area to preclude crushing. And here's a case where crushing occurred. The stress was going this way. They crushed that concrete, and here's that plate. The plate kind of goes like that. They just kind of put it over there so you can kind of see, the concrete is on this side of the shear lug. It just flipped over. That's what you're looking at there. That's kind of what that looks like. So you're wanting to avoid that. And if you're not getting enough area, stiffeners can get quite thick really quick. The deeper you go, you can put a stiffener in to increase your bearing area so you can get around this problem. So there's the same thing. There's same thing in the previous page. Just kind of, if I got a shear in one direction, just because I have a really deep plate, it's really the thickness of that stiffener is how much bearing area I can take. So it's 2 times the thickness of that the lug. And so just because I go deeper doesn't mean I get to use all of it. I can put a stiffener in, and then I can start to get more area here. So there's little things you can play there to increase bearing area. And then, of course, the breakout is very similar to anchor bolts. It's 35 degrees off the side of the shear lug, and then, of course, it goes down at an angle of 30 degrees off of this plane down, and that is your breakout area. Very similar calculations to the anchors. You do have to subtract the area of the shear lug, however, kind of a small little caveat in there. But I'll say this, when you use shear lugs, it's not really going to help you on the top of a pier, right? Just because I put a shear lug in there, I just don't have enough concrete, right? So you're having a lot of problems. We're talking usually industrial problems. We're talking about, 20 by 20 by 5 feet deep, things that you're anchoring into. I really have some room to get, I'm transferring a lot of shear into a large area of concrete, but so it's usually industrial applications, but it's something you'll probably run across at least once in your life, and there are now requirements to help you do that. So any questions on that? I can show them the last code. Oh, yes, sir.
Sorry, is there an approach in 318 for the grout offset?
Yes, there is. So if your base plate was above, so your concrete, the top of your concrete, and you have a grout, 2 inches of grout on top of it or something like that, the breakout is only to the top of the concrete, right? But when it gets to things like shear lugs, yes, there's a lot more information in 318 that talks about how do you treat, at least for the shear lugs, the bearing area. Same thing for like shear for anchor bolts, just for shear checks. There is a requirement in there that says, if you're, it gives you a reduction in your steel capacity for being further off the top. So there are requirements in there for having a grout pad for shear in most conditions.
So it's not requiring you to hook it bending the bolts.
You can do that, right? But no, I think it's just like a straight 20% reduction up to a certain height, like 2 inches or something like that. I'm going from pure memory on that, but so like it's a factor of 0.8. So if you really wanted to get into that, I think there are other pubs. Actually, I'm going to say AISC in their anchor. Now it's been a long time since I read it, but I thought if they got into different ways to calculate, because there's a couple failure modes in steel. If you're just looking at that, especially like if there's no grout at all, right? But if I remember, I don't know, is it AISC's Guide 1 is on Anchorage, I think it is. I think it has more information on that. Okay, thank you. Yes, sir.
So for Anchorage configurations that are, say, at a set spacing over a great distance or a set area in 2 dimensions, I always struggle with how to kind of incorporate the group effect and build and break out failure surface with those types of scenarios. So I was wondering how you tackle that.
Well, I mean, quite frankly, yeah, no, there is none. So if you really are spacing out their anchors, they just act separately.
But what if they're tight enough, though, that there is a group effect that you have to consider?
Then that should be easily calculated. I guess I have to see your exact layout to help you out a little bit more. But once you get the spacing close enough, once again, you're not calculating. So if it's shear, right, towards an edge and you have the anchor, you calculate the 35 degrees on the outside, but all of those anchors, if they're within that spacing, you just draw a straight line. You don't calculate every little jagged edge. You just take a straight line across the back. Okay? And that makes the calc very simple, I believe. Okay, good. Wasn't sure I was going to get that one. So, any other? Yes, sir.
We have 2 different Anchorage for bars in the bar development like the 19 degrees as a food, and we have different equations for casting place anchors.
Right.
When we follow these 2 guideline equations, we have 2 completely different capacity.
Right.
What's the concept?
Okay. So he's got right to the heart of a big issue. So what he was saying is, okay, I have a hooked anchor, or I have a 90-degree hook, that I'm developing in regular steel, right? We have a development length equation. And then I have say like a J hook that I might have for an anchor. And they go, well, why wouldn't I have the same either development or capacity? Bottom line is you shouldn't. Remember when they built the 318 code, so if you want to bear with me, and if you get tired of this conversation, just let me know. But the way the 318 code was made was, okay, I have a bunch of typical situations. I have a moment frame or a structure, I have a 2-way slab, I have 1-way construction, I have a certain beam and column size that we typically use construction over the years. And so, when my beam comes into my column, and I put a hook in there, well, I always got a little bit of compression in there, right? Because the dimensions of the beam and the column over the years, I'm always getting a little bit of compression field acting on that hooked anchor. And so they use that. And then they would find, oh, in this case, you might need to put an extra tie here. Or in another case, you're at the column and a beam at the top corner. You put 3 hairpins in like this and put 2 hairpins in like that. Why? Because they're having the same problems. If you had no reinforcing steel, you get the exact same failure. If you built that column and that beam and put no reinforcement in it there except for the hook, you'll get the exact same failure at the exact same load as you would get from a Chapter 17. But you're never in a building without reinforcing steel, so it's inherently in the code. And so that's why half of the code is detailing. Is because they made these values divorced. There's compression fields acting on all those development lengths in the values that they give you. Do you guys all know what I mean by these compression fields? I mean, if I have a beam coming into a column, it's bending, right? That's where the moment's coming from. So half of that beam is pushing on the column, the other half is pulling. I am putting compression into that column. I am putting a compression field on the development, on the tension side that's trying to pull out. So the code grabs it without telling you that. And so what they're doing right now, we can get into the semantics of it, is there's up to a 40% difference in the values depending on the configuration and the steel that they're using. There is a 318 sub R that is currently working to resolve that inconsistency. So because that is something the steel industry has been mad at us forever, right? Because they want to attach a steel beam to a concrete column, and they have to use the anchorage requirements of Chapter 17, and they get all the benefits of this modified development length that you get out of using the rest of the code. So they're trying to bridge that gap. Okay. Because, you know, that it all comes down to compression fields.
When it comes, for example, to connection of column footing.
Oh, yeah.
Mat footing, but you have almost the same behavior. Like a fixed connection, faceplate, and a column fixed connection.
Yeah.
To mat footing in concrete building and steel buildings.
Yeah.
But the answers are completely different in terms of capacity.
Right, so he's asking about like a column coming down to a foundation. So if you look closely to what the code is saying is if you're doing a cast in place, they make you take that longitudinal steel and bring it all the way down to the far side of the footing and then bend it, right? And what they're doing is they're engaging the footing, right? They're not just anchoring the steel, they are facilitating the dragging of the load into the footing. That's what these detailing things are doing for you. They're detailing you into a better result without you having to run the numbers. Whereas if you attach something to the thing, now all of a sudden you got to run the numbers and things don't seem to work out the same, right? The big worry out there right now is maybe not that so much, although it's unfair to the steel industry or anyone who's attaching because the values don't make sense. And like I said, there's a committee they do want to resolve that issue. So we'll see how that all shakes out. The scary one, though, that we've not all, remember I showed you that anchor that pulled out, had the reinforcing steel on a plate, and it still pulled out, and it just was stuck in a regular piece of open steel. Well, think of a very large shear wall, high seismic. So something that's 20 foot wide. The compression field, so these development length equations, I'm kind of assuming there's a compression field acting on that. But the compression field is 20 feet away. And now this thing's turning over, yet I'm only embedding that reinforcing steel, possibly just the development length, right? That is a concern. That it kind of makes you real nervous at first thought, but then you start, and this is the out that happens in committee is, oh, but you have to put in this steel here and that steel there, and it'll take care of that. But it still makes you pause, right? Because people build things in so many different ways. It's the beautiful thing about concrete. If the person isn't thinking about that, there might be a case where a serious failure could occur, a very serious failure.